So again, today we're going to be working on exponentials in real life and modeling their data points. So we're going to be using StatEdit. But if you kind of look down on your notes that you picked up for today, what do you notice about like some of the problems? I've already done them. Because I think sometimes we'd spend too long on notes and not enough time on actually practicing. So we're going to not speed through notes because I'm still going to teach you. But we're going to go a little bit quicker so that we have more time to just practice and fumble through doing the buttons on our own calculator instead of as a class, me not seeing the mistakes that we're making. I was going to make a second point, and now I can't remember what that point's going to be, so I'm just going to keep talking. So in exponentials, sometimes data from an exponential function does not actually display a proportional growth pattern. Remember that proportional growth pattern is what we're talking about, like how it changes. So it's the number we can multiply by. So when we did our sequences, we always found the pattern and we're like, dope, this is a geometric sequence, which means it's an exponential. But exponentials can be transformed on your graph. We can shift them up and down. Last time we talked about shifting them left and right and horizontally dilating them, which is the same as vertical dilations. Horizontal translations is the same as vertical dilations, yes. But we never talked about what happens when you vertically translate something. And vertically translating a graph is going to get rid of the proportional relationship, which means they're kind of tricky graphs to make sure you realize that they're exponentials. So if we found that number, the constant that we're going to add or subtract from the output values, it's the y, we will reveal a proportional growth pattern, which will then tell us that initially our function was exponential. We've just shifted it up or down some number. So I'm telling you right now, these three tables are exponential. But if we went to go look for the proportional pattern, what number would get me from 7 to 13 if I'm using multiplication and division? 13 over 7. And then if I did this one, it'd be 25 over 13. Those are obviously not the same fraction. They wouldn't reduce to the same number. They don't reduce at all. So we're kind of like, well, last class we would have said this is not exponential, but I'm telling you it is. Because what if we just adjusted these numbers by doing the following? What if we just took this output value and we subtracted 1? Okay, don't overthink it. What's 7 minus 1? What's 13 minus 1? 25 minus 1? 49 minus 1? 97 minus 1. What's happening with these numbers as I look for that proportional growth pattern? How do you get from 6 to 12? Times 2. And 12 to 24? 24 to 48? 48 to 96. So we do actually have an exponential function here. We've just transformed it. So we know what number we'd have to add or subtract, but if we want to go actually write the original function, we're going to have to do a little bit of work. Okay, we're going to call this function that we wrote k of x, the one where we said, okay, subtract 1. I only picked k because the letters F, G, and H were used in this example, so I just picked a random letter. My first name starts with K, so we're going to use a K. Okay, whatever, it doesn't matter. Okay, so we're going to say k of x was equal to g of x minus 1. That's what we wrote, not g of x. That function is named f. So f of x, my bad, minus 1. Okay, well, if we only look at k of x, which is all the numbers we wrote and changed in our table, what's the initial value for k? 6, because it's partnered with 0. So we know k of x could actually be 6 times that common ratio, which was 2, raised to the x power. Let me get the right color code here. So again, that's the pattern we saw once we subtracted 1. But that's equal to the original function minus 1. If I wanted a formula for the actual original function, I just need to solve for f of x. What do I have to add to both sides to get f of x to be by itself? I just have to add 1 to both sides. So we would say that f of x is actually equal to 6 times 2 to the x power, all of that plus 1. Notice it's back at the end. I don't actually add it with either of those two numbers because when we did vertical transformations, it was always tacked on the end of the function. Yes, sir?
Can you go to the top? Because I missed the highlight.
Yes. You're welcome. I'm actually going to change this color code because I'm realizing that this might be confusing. So we'll make this 6, and we'll make this initial value blue, which means this number should be blue. I think that's a little bit clearer on my color coding. Sorry about that. Okay, so again, finding the number you're going to multiply or divide by is a little bit tricky because you just got to think about numbers and how they multiply. So just silently thinking, because it's going to take you more than just a quick little look at it, what number am I going to be able to add or subtract to the output values of g of x here to make this a proportional pattern that I recognize changes by, don't say anything out loud, just think for a little bit, because it didn't come to me at first either. Anybody got an idea? Yeah, what's up? 2. If we add 2, so we're saying that the new function we're writing, k of x, would be equal to the outputs g of x plus 2. That would make this 4, 12, 36, 108, and 324. What is that pattern, or how am I changing in the new outputs we created? Times 3, times 3, times 3, and times 3. Okay, so let's write an actual function for g of x. The things we know that this function we named k of x, again I just picked k because YOLO, is going to be g of x plus 2. But I also know that k, the numbers I added onto this table, would be created from an initial value of 4 multiplied by that common ratio of 3 raised to some x power. Very easily, how do we solve this for g of x? Subtract 2 from both sides. This is going to be 4 times 3 raised to the x power, all of that subtracted 2. Okay, part C is for you. I want you to, again, look at that table, see if you can figure out what number you can add or subtract to make it a proportional relationship, and then write the function for h of x. If we add 1 on this one, nice. Okay, so here's what I would write down for this one. I would say k of x, again, I just randomly chose a letter for that. It doesn't have to be k, I like that letter, personal preference. Is h of x plus 1, which would make this 64, 32, 16, 8, and 4. Ooh, that's a power family we've been practicing. The way we change from one number to an x is multiplying by a half. Multiplying by a half, multiplying by a half, multiplying by a half. As a little bonus,
We can't do divide?
multiplying by a half is the same as dividing. It's just easier to see the plain number that you're going to write in the function instead of divide by 2. Because otherwise you might put a 2 there, and then that means multiply by 2. As a little bonus, if I didn't want to write this as a fraction, how else could I write this number to still indicate 1 over 2? True, maybe with a base of 2. Somebody had this on a flashcard earlier. No. Okay, I'm moving it from, there I heard it. I'm moving it from denominator to numerator, so I make a negative. So this is the same as multiplying by 2 to the negative 1. That was bonus extra, but I think it's helpful to start remembering that fractions, the numbers in the denominator, can move to the top by making the power negative. Okay, following the steps we did before, we would say that we know that k of x is equal to h of x plus 1, and k of x is written with an initial value of 64. So that would be 64 times the common ratio of 1/2, all of that raised to the x power. We quick solve for h. We'd have h of x equal to 64 times 1/2 raised to the x power minus 1. But I'm going to tell you, I'm going to do a little bit extra. Because right now this is showing me a fractional fraction base. Last class we talked about how to change the base. We already discussed that 1/2 can be rewritten as 2 to the negative 1 raised to the x power. What does that mean I can do with this part right here? I know this is bonus. If you stopped just a second ago, you technically did what I asked, but I couldn't help myself, and I'm doing more. The reason I want to do this is because these are equivalent expressions. These are exactly the same, and that's what we did last class when we worked on changing the base. The reason I wanted to do this is because potentially I could be asking you what kind of horizontal translation occurred here. You don't see a horizontal translation. But what is this horizontal translation? Translation is the wrong word. Transformation is occurring when there's a negative in the exponent. What happens when you put a negative inside a function? It flips which way?
The other way.
The other way. So normally it reflects over the x-axis, so this one is reflecting over the y-axis, which is why I went from decay to growth. If you can remember those words. Yeah, go ahead. Okay, so what we're going to be doing today is modeling exponential functions with data, because we just saw how we can do this by hand, and it's kind of clunky, because we look at these numbers and we're like, oof, dear, what are we doing here? We have to do all of this stuff. So instead, we can just look at it as if there's no vertical dilation, but we just have different bases and powers. They're not going to be cute numbers today because we're going to be using real life data and not trying to get it into a perfect number I can multiply by, like times 2, times 2, times 2. It's going to be decimals all day today. For me, you round to 3 decimals. How many decimals? 3. So when we round today, it's going to be 3 decimals. There will be one time I round to like 5 decimals because the number is kind of weird, but that's a fluke. In example 2, again, let me read this little box for you. When we model exponential data and functions from, let me try all of those words one more time. Modeling exponential functions from data can happen in 2 ways. We've technically already done it, finding the common ratio and the initial value. That's what we just did in the tables. That's easy. But when the data is not super set up for you, or you're just given 2 input-output pairs and you don't know the common ratio, we can actually do this algebraically or with technology to write a regression for this exponential data. We're going to do it with technology today because we have not actually learned the algebraic skills to do it by hand, but eventually we will do it by hand. This is something you'll see on free response questions on the AP exam, is being able to do this by hand, but we haven't learned how to do that yet. So we're going to use technology. So just to make sure we understand what we're given these kinds of questions, example 2 is basically just setting you up for success for the future. It says, for 0 to 30 minutes, the number of fans inside a large sports stadium can be modeled by the exponential function f of t equal to a times b to the t, where f represents the number of fans, f for fans, makes sense, inside the stadium t minutes after the gates open. There are 47 people in the stadium 2 minutes after the doors open, and there are 2,602 fans inside the stadium when 20 minutes has happened. What? 20 minutes after the doors open. So here's what I know. I know that if we're looking at coordinate points in this problem are given as time, comma, fans. So minutes, comma, fans. So if I look at the information I was given, I was told 2 minutes, 47 fans, 20 minutes, 2,602 fans. So I have these 2 input and output pairs, and I can write equations for this exponential. Again, this question right here is setting us up to be able to do this by hand later. We don't have the skills yet to do it by hand, but there will be a free FRQ question on a test that makes you do this by hand. It says, write 2 equations that can be used to find the values for constants a and b in the expression f of t. What did I do here in the problem I already wrote down for you? Where did those numbers come from that I put there? Yeah, I have an output of 47, so I put that where outputs go. That's where F is. That's the fan number. And I have an input value of 2, so I put that where the input value is, T for time. In the other equation, I was given a fan value of 2,602 and an input value of 20. So I just plugged in two separate equations, the input and output values in. Right now, we don't have the skills to solve for A and B by hand, but you can actually do it. It's not terribly difficult. We just haven't gone over logarithms yet, which is required to solve them. So what we're going to do today, instead of doing this by hand, which again, this is setting you up to be able to do it, we're going to be able to do this using a regression tool. Now, we've done stat edit before, so let me remind you of a few things. This is on that calculator sheet I gave you. I think it's purple. Before we do any sort of regressions, what should we always turn on in our calculator? Ooh, we don't remember. You press mode. You scroll down to where it says stat diagnostics, and you make sure that you turn that baby on, because we need our stat diagnostics on for the AP exam. So on your calculator right now, please do that, or else yours will look different. It might already be on, which means you didn't reset your calculator. You should always reset your calculator when you pick it up. But just like when we did this for polynomials, you type in the data, you go to stat, you go to calculate, but this time you're choosing option 0. Which option?
0.
On the yellow calculators, it does not show up on the regular screen. You have to scroll down. On the newer ones, it might actually make it on the regular screen, but you can just press 0 for exponentials. You're going to scroll down to where it says y1, and you put y1 right here. Does anyone remember how to get the y1? Alpha trace. Enter. Then we go down to calculate, and you get this screen. You would use the A value here and the B value here to write your regression. How many decimals are you going to round to? 3 decimals, thank you. Now you're probably like, we haven't talked about what these numbers are right here. It's going to come up later on in this unit, but it's called a residual. If you're in stats, you may already know what that is, but that is a residual, and we'll be talking about that later. I want to bring that to your attention so you're not shocked when we start using the R squared number. It's called a residual. But do we feel like we can do this? Yes? If that's the case, example 3 on the back is for you. I have a table for you there. I want you to first write 2 equations that can be used to find the values of constants B. I guess I should flip to that question. And then I want you to find the values of A and B. We're going to use technology now. Later we will do that by hand, which is why step A is there, to help you remember that normally when we're doing this by hand, you will write the 2 equations and do something with them. We don't know how to do that yet. We will get there. Number 3 is yours. I'll give you some time. Okay, our 2 equations should use the input and output values from the function and then leave A and B there, which means we should write something that looks like this. So we should have, I'll write it in red so you can see it, 21.54 equal to A times B raised to the 3rd power. And we should have 3.62 equal to A times B to the 8th power. As a little bonus here, is this going to be growth or decay? Decay. Why decay? The outputs are doing what? Shrinking. Plus, when you write the regression, you should notice something about the B value. When you use technology to write this, your calculator should have spit out the numbers to you that g of x would be equal to 62.801 times, and if you rounded correctly, 0.7. But does a lot of 9s in a row. I want to show that number just because this is my notes. So I want to be like, where did that 7 come from? Yeah, 5 decimals. I know I said that it should be 3 decimals, but 0.700, whatever. Anyways, did we get these numbers? Did you round it to 0.7? Yeah, cool. Actually do that. That's 3 decimals, but I just wanted to show this on our notes. Again, this number here, the B value, is less than 1. That would show us its decay. That makes sense since these numbers are getting smaller. Those are the quick checks we give ourselves to make sure we're on the right part. Moving on a little bit, you've talked about this before in Algebra 2, but there is a number E. It's called the natural base E, or Euler's number. Euler's name spelled like this. That's why, it looks like it's Euler, but it's pronounced Euler. This is Euler's number. It's a number that shows up so often in mathematics, we stopped writing it out, and we gave it a letter, kind of like pi. But it's E. It's going to help us show a lot of things that grow or decay in real life. So population growths of bacteria changes naturally, so that's base E. Continuously compounding interest is base E, so shows up more often than not. So I've done most of this problem for you, but I still want you to practice a little bit. It says the number of bacteria B in a particular culture can be modeled by the exponential function B of t equal to 17 times E raised to the 0.31 t, where t is measured in hours. It says let A of t equal to A times B to the t be an equivalent expression for B of t. Find the value of A. That was easy. A is the initial value. What's the initial value here? 17. That means we started studying this bacteria with 17 different bacterias in our little petri dish. As a bonus, the B value is E to the 0.31, basically not t, which is approximately 1.63363. That's a little bonus for you. Part B says find the average rate of change of B of t over the interval from 1 to 7 hours. I want you to highlight, circle, star, underline the words average rate of change. This was like the first concept we learned in this class. Do we remember doing this? Average rate of change is like finding the slope. And I know that exponential functions are curves, which means they don't actually have slopes. I know this. But we can still find that average rate of change between 2 points by using the formula f of the first, or I guess this is b of the second input minus b of the first input all over the second input minus the first input. The input values they gave me were 1 and 7. So let's figure out what this actually means for me to do. B of 7 means that I want to write the function 17 times e raised to 0.31 power, but not multiplied by t anymore, multiplied by what? 7. B to the 1 means I want to type in 17 times e to the 0.31 times what? 1, all over 7 minus 1. This is the inputs and outputs for this function at 2 particular points. We're just going to find the rate of change between 2 points. That looks like a hefty kind of problem, but at this point, you're putting this into a calculator. Start with the fancy fraction, unless you're good with your parentheses. Whoa, oh my gosh, words are not working today. We fancy fraction this, and we type everything all at once. So I will type along with you once I see people stop writing, so you can see what this might look like in a calculator. So the average rate of change between hours 1 and 7 is 20.952 bacteria per hour. So those 17 pieces of bacteria are multiplying or are changing by 20 every hour. Gross. But another question I can ask you with this sort of information is to find the value of t, so find the time, I'm asking when. The number of bacteria in the particular culture is 1,000. So this time I'm giving you the output. I'm giving you B of t. Your job is to find t. Now again, we don't know how to do this yet by hand. We haven't learned quite yet. So what we're going to do is, again, use technology to do this. You are going to type the first part of this equation into y1. You're going to type the second part of this equation into y2. So this should be y1. This should be y2. When you do this, you're going to get a graph or a picture that looks something like this that I've graphed on the screen or written on your paper. You are looking for the place where these two the curve and the flat line intersect. Does anyone remember on your calculators the buttons you press to do an intersection? Intersect. Well, yes, but what menu is that on? It's not in mode. Second trace, which is the calc menu. Yeah, second trace 5, and you enter. So I'm going to give you a second to try to make this work, because when you open your calculator, if you don't zoom to the correct window, this is not working. I don't recommend just zooming out. I recommend adjusting your window. You need to see an output of 1,000. So change your output, your Y value, to something bigger than 1,000. I'm going to give you a second to think on how to do that, and then I'll show you on my calculator. But we've done this before. I just want to see if you can reach back and find that information. We should get that the intersection point is 13.144, comma 1,000, which means that the number of hours is 13.144 hours. Yes. Yes. Example 5 says, after 50 deer were introduced to a large wooded area, the population of deer in the wooded area can be modeled by the exponential function d of t equal to a times b to the t, where t represents the number of years since the deer were first introduced into wooded area. The population of deer increases by 13% each year. Here's some things to remember from Algebra 1 and Algebra 2. If we're talking about increasing values, we're talking about growth. The way that you decide the b value when you're given a rate of growth or a rate of decay is here. I wrote it down for you. B is equal to 1, either plus or minus that rate, but you put that rate in there as a decimal. Plus is growth, minus is decay. Makes a lot of sense. So for part A here, it says find the values of A and B and use these values to write an expression for D of T. So our A value is our initial value. How many deer were initially in this wooded area? 50. And our B value is going to show that we've increased by 13%. So it's 1 plus 0.13, which is 1.13. That means that D of T is equal to D of T equal to 50 times 1.13 raised to the T power. Part B asks you to use the model, according to the model found in Part A. What is the population of deer in the wooded area after 6 years? Well, years is how I'm measuring time. So all I need to do is plug in 6 for time. I know that T is time. It literally says number of years. If it had said months, we'd have to do something different and convert that. But we're just doing 50 times 1.13 raised to the 6th power. I'm trusting you can type stuff into your calculator. That is 104.098 deer. That's about how many deer are going to be in the large wooded area. Obviously, you'd round that to 104 because you can't have 0.98 of a deer. That's weird. But for your notes, so you don't ask yourself, where'd the 104 come from? Or write down the whole number. Part C says, find the time D when the population of deer in the wooded areas is expected to reach 5,000. If I'm telling you the population, I'm telling you the output. That means D of T is equal to 5,000. So D of T, which is 50 times 1.13 raised to the T power, would be equal to 5,000. Again, at this point, we don't have the math skills to solve for T. We eventually will, but not yet. So we're going to turn to our technology to do this. We just went over a question on how to do it, and you'll have plenty of practice time later. So we are going to graph both functions, and we're going to see where these two lines intersect. Again, you're going to have time to practice this later, so I'm just going to trust that you can look at your notes and see what you did. You find the intersection point. You will have to adjust for your window settings, but your intersection point would be at 37.68, comma 5,000, which means that the answer to this question, the time T, is 37.68 years. Again, you're going to discover when you practice if you actually know how to do that, because I've shown you multiple times already how to adjust the window. But part D is really important for us. It says, find an equivalent expression for D of T where T is measured in months instead of years. Okay, Our equation is measuring in years. We want to adjust this equation to measure in months. Don't overthink this. Well, maybe overthink this. 1 month is equal to how much of a year?
12.
1 month is 12 years? 1 over 12, because it's 1/12 of a year. Yeah, gotcha on that one. Definitely had to overthink it a little bit. So what we're saying is, if we want to adjust our equation to not measure in years, but to measure in months, we're going to have to rewrite it so that it says d of t equal to 50 times 1.13 times t divided by 12. Ooh, okay. Do we see where the divide by 12 came from? If we're wanting to measure in months, but originally we're measuring in years, 1 month is 1/12 of a year. If we utilize what we learned last class about how to adjust when you have a horizontal dilation, we're going to take that value and we're going to separate it from the t and put it inside the b value. Calculator time. What is 1.13 raised to the 1/12th power? AKA, what's the 12th root of 1.13? We should get 1.010. So we have adjusted this function so that we are now measuring in months instead of in years. So you find the factor that changes it from what you're measuring to what you want, and then utilize what we learned last class about changing the base.